we are going to start the process of learning how to make Lewis structures. And we're going to do this with 3 different molecules. And the things we're going to work with here are NH3, CFHO, and CO3 2-. So those are the ones that we're going to use for our first round here. Your steps for doing this are to kind of work your way down this in order. And we're going to do these 3 together, and then I'm going to give you some time to build some of the other ones with the model kits and get them drawn onto the paper as well. So step 1 is to determine the total number of valence electrons in each one of these things. So we do that using the periodic table and some of the shortcuts we've learned. We've learned that everything in the first column has 1 valence electron, second column has 2. We skip the middle, 3, 4, 5, 6, 7, and 8. So with NH3, nitrogen has 5 valence electrons. We have 3 hydrogens at 1 valence electron. So NH3 has 8 valence electrons. With the second one, carbon has 4 valence electrons. Fluorine has 7 valence electrons. Hydrogen has 1 valence electron. Oxygen has 6 valence electrons for a grand total of 18 valence electrons. And for the CO3, you've got carbon at 4 valence electrons, 3 oxygens at 6 valence electrons each, and that -2 charge means we have a spare 2 electrons. So 18 and 2 and 4, 24 valence electrons. So now we're going to build just a pile for each one of these, of pieces. Don't try to arrange anything. Just try to build, like just make a pile. So like here's 1, 2, third oxygen, 3 oxygens, a carbon, and now 24 electrons, so that'll be 12 pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, there's that pile. So for each one of your molecules, we're just going to make a pile of the pieces it's going to take to get it done. So here's chlorine, an oxygen, and a hydrogen, and a fluorine, and 18 electrons, 6, 8, 10, 12, 14, 16, 18. Okay, there's that set. And my NH3, here's a nitrogen, 1, 2, third hydrogen here. Third hydrogen, and 8 valence electrons. 1, 2, and 3. Okay, so now I have 3 different piles of stuff to work with. The next thing says to draw a skeleton structure arranging the atoms around a central atom. Here are the general rules. Hydrogen's got to be on the outside. Hydrogen can only make 1 bond. It's the end of your molecule, so don't try to put it in the middle. Generally, the least electronegative element is going to go in the middle, and some molecules, especially those with more than 1 carbon or more than 1 nitrogen, may end up with more than 1 central atom. So we're going to take each of these little piles, and we're going to arrange the molecules, or arrange the atoms. So with the NH3, go up so I get a little more space. Since all we have is nitrogen and hydrogen, the nitrogen is going to have to go in the middle with the hydrogens clustered around the outside. And I'm going to leave the little pile of electrons for this molecule kind of sitting off to the side. Okay, my next little collection. I have C, F, H, and O. I first need to make a decision about who's going to go in the middle. Well, that's where my magic words are going to come in handy. So I'm going to look at my magic words, FOCLMBRISCPH. Hydrogen has to go on the outside, so carbon is the least electronegative. The least electronegative tends to go in the middle because that's your element that's the most willing to share. It's the least selfish, so we put the least selfish element in the middle, and then we're just going to take the rest of them and put them around the outside. Now, it does not make any difference how you put them around the outside. You can put them like this, like this, like this, like this, okay? So it doesn't really make any difference how we do this. So just get them clustered around the outside in some way. And then my last one is CO3. Here's my pile of electrons for this group. Dump them down there. Then I've got my CO3. Carbon is less electronegative than oxygen, so I'm going to put the carbon in the middle and the 3 oxygens around the outside. And here's my electrons for that. Okay, so arrangement of elements goes first. Now notice that in my piles of electrons, I've made no attempt whatsoever to decide which electrons came from which atoms. It's just like, here's a pile of electrons. Let's go ahead and use them for the common good. In using the electrons for the common good, we have a priority. The next bullet point on your list says, connect each atom to the central atom with a single bond, or 1 electron pair. So out of my pile for NH3, I'm going to use 3 electron pairs to hold the molecule together. Use 3 electron pairs to hold the molecule together. And over here again, use 3 electron pairs to hold the molecule together. So that's obviously got to be the first priority for the electrons. We've got to hold it together. Next thing on the list, distribute electrons as lone pairs to the outside atom, completing an octet around each atom, except hydrogen, which only wants 2 electrons. Well, the only outside atoms on NH3 are hydrogens, and they don't want 8 electrons, so we're not going to do anything else with that one. Over here, I'm going to give 3 electrons to the fluorine. So now fluorine's got access to 8 electrons. The hydrogen doesn't need any more. I'm going to put electrons around the oxygen. And now I've basically spent my whole pile. And then over here, we're starting to kind of crash into one another. There, there, and there. Whoops. Some here, some here, some here, here. Okay. And then it says if you have any remaining electrons, put it on the central atom. So in the case of my NH3, I had some electrons left over, so I dumped them in on the nitrogen. These other 2 piles, I didn't have any leftovers, so I haven't got anything to dump on my central atom. Here we get kind of a heads up. The central atom can occasionally end up with more than 8 electrons if that atom has a valence shell of 3 or greater. So if you still have more electrons left, you're just going to dump them on the middle. They're going to get stored in the d orbitals, and that's why it has to be 3rd energy level or greater, because we have to have a spot to store them. Now it says, rearrange the electrons on the outer atoms to make multiple bonds with the central atom in order to obtain octets wherever possible. If there's more than one way to do this, use formal charge to determine the best possible structure. For equivalent possibilities, draw all of the possible resonance structures. Now, I am going to tell you a couple of hints about this rearrangement rule where we have to move things around. Okay. Generally speaking, when we have to make multiple bonds, this multiple bonds business the carbon, oxygen, nitrogen column elements is going to be the best situation. If you can avoid multiple bonds to the halogens, we're going to try to avoid multiple bonds to the halogens. The formal charge thing we'll worry about in a little bit because we don't need it right away to do this. So later on, we're going to look at formal charge, but it just complicates the issue at the moment. So in the case of this one, carbon doesn't have an octet. So we're going to take one of the pairs from the oxygen and we're going to pull it in and create a double bond between the carbon and the oxygen so that now carbon has access to all of those electrons and oxygen has access to all of those electrons. And in the case of our carbonate ion, we're going to do the same thing. We're going to pull one set of electrons in off of that oxygen to get an octet for the carbon. Now that we have these nice pretty piles on our desk, we're going to draw them onto this paper. So if you look at your NH3, our NH3 currently looks like this. If we do a quick assessment of our situation, we can see that the nitrogen has access to 8 valence electrons. The hydrogen has access to 2 valence electrons. And so we're good. We've created a structure that works. Most often, when they draw the final cleaned up version of these things, they tend to use lines for the bonded electrons and dots for the non-bonded electrons. So you will often see this drawn as nitrogen bonded to hydrogen, bonded to hydrogen, bonded to hydrogen, with a lone pair of electrons on the nitrogen. Remember that one line is equal to 2 dots. So my other one, I had to look and see what order I had it laid out in. My other one, I have to draw it down here a little bit. I've got a carbon, a fluorine. I've now got 4 electrons between the carbon and the oxygen only has 4 lone electrons, and a hydrogen down here. So if I do a quick assessment of my situation, here's carbon, which now has access to 8 valence electrons. Fluorine has access to 8. By doing multiple sharing, oxygen has access to 8. Hydrogen has access to 4. So if I redraw this to look nice and pretty, I've got a carbon double bonded to an oxygen, single bonded to a fluorine, and single bonded to a hydrogen with lone pairs of electrons around the fluorines and 2 lone pairs on the oxygen. So redrawn it looks like that. And my carbonate ion, I've got a carbon in the middle. Bonded to an oxygen. In this case, we put 4 electrons between the carbon and the oxygen. And then down here, and here's 8 electrons for the carbon. Eight electrons for that oxygen. 8 electrons for that oxygen. 8 electrons for that oxygen. And this one needs something that the others don't have. The thing that this needs that the others don't have is a pair of brackets and a -2 charge to say that this whole mess has 2 more electrons than it should, and you're going to see those square brackets with the polyatomic ions. So on the redraw, this thing now is carbon, double bonded to an oxygen, single bonded to another oxygen, single bonded to another oxygen, with a 2 negative charge. So there it is, kind of cleaned up. Now, I do have a little smidgen of bad news about this guy. It's a just fine structure, so that's not the problem. However, we could have done it in more than one way. We had to make a decision. When we were at this point, we chose to move the electrons in off of this oxygen. We could have done it with the oxygen down at the bottom. Or we could have done it with the oxygen off to the side. The really horrible news is if you had to make a decision like that, when it's time to draw it, you actually have to draw all the possibilities. Now, it's going to end up only being 3 possibilities, not 9. We don't have to do like, what if I moved this pair? What if I moved this pair? What if I moved this other pair? But I do have to do, what if I put it in this position? What if I put it in this position? What if I put it in this position down here? So here we go. This was the possibility that it went with the top oxygen. And we're going to connect the possibilities with double-headed arrows. So instead of doing the double bond with the top oxygen, we could have done this with the side oxygen. Or, we'll go this way with it, we could have done it to the bottom oxygen. I didn't make the rule. I just have to be the bearer of the bad news that you have to draw them all. This complete collection of all the equivalent Lewis structures is called resonance structures. Lewis structures that have different possible ways to arrange the electrons. And so we have to draw them all. It is not a rearrangement of the atoms. So we don't have to try the atoms in all the positions. We just have to try out the electrons in some different positions. The reason we have to draw them all is that the actual structure is an average of the possibilities. And if not all the structures are equivalent, the more preferable structure makes a greater contribution to the charge. In terms of how they know that it's an average of all the possibilities, it comes back actually to bond length. We have a device called an X-ray crystallography machine that can measure the length of these bonds. And if they measure the lengths of the bonds in a carbonate atom, they find out that all three of these bonds are the same length. We just learned that single bonds are longer than double bonds. So if this is two single bonds and a double bond, it would be two long bonds and a short bond, but it's not. Instead of being two long bonds and a short bond, it ends up being three bonds of equal length, all of them that are a length equivalent to what would be a bond and a third. So it's a little shorter than a single bond and a little longer than a double bond. And the answer is actually that this set of electrons resonates between the three possible places. It spends equal time in all three places, and those electrons move around. And so the average of these three structures is what the actual structure for a carbonate atom looks like. Okay, before we jump to formal charge, we're going to take some time to practice drawing some Lewis structures. And I want you for now to make use of the little paper kits while you do this. On the back of your sheet that you took some notes on from your textbook, there are some molecules. I would like you to build Lewis structures on your desk for all these molecules. Once you get the molecule built and you're satisfied with your Lewis structure, I want you to draw the Lewis structures onto this piece of paper. So you're headed toward having a collection of Lewis structures. Okay, take some time to play with your model kits and build some models. Hit pause on that. If you're not quite done, that's fine. And add to our arsenal here a decision-making tool. For example, with this NO2 positive that you made and its 16 valence electrons, the way I see it, there are actually three different ways I could have gotten this done. I have three different resonance structures here. I could have done two double bonds, but I could have done kind of this ever awkward single bond, triple bond combination. In the rules about resonance structures, it says the actual structure is an average of the possibilities. If not all the structures are equivalent, the more preferable structure makes a greater contribution to the average. We need a way to decide, when I'm looking at lots of possibilities, what does it mean to be more preferable? Chemists have invented a tool to help them decide on the more preferable versus the equivalent of Lewis structures. And it's called formal charge. Formal charge is merely a hypothetical. It's the hypothetical charge an atom would have if in a molecule if the bonded electrons were distributed evenly. It's created by chemists to help predict the arrangement of atoms in a molecule and which Lewis structures will be more preferable. So we need to kind of make a list of what is going to be the more preferable situation for formal charge. The most preferable situations for formal charges is you want to create a structure that has the lowest formal charges. So if you can create one where everybody has a formal charge of 0, that's better than creating a structure where one of them has a formal charge of 1, one of them has a formal charge of 0, and one of them has a formal charge of +1. So we want to try to get the formal charges to 0 if possible, and if we can't get them to 0, try to get them as low as possible. Formal charges of like +3, -3, not good. We want to try to rearrange the electrons to make that not happen. And we want a situation where the most electronegative element has the negative formal charge. Now, obviously, if you can get everything to zero, we don't have to worry about the second criteria. But if you can't get all the formal charges to zero by arranging the electrons in a way that can happen, when you do arrange the electrons, you want the negative formal charge to land on the more electronegative element in the molecule. The textbook method for calculating formal charge is going to tell you to take the number of valence shell electrons in the free atom, subtract the number of lone pairs, and subtract 1/2 of the number of bonding electrons. That does work. I'm not a big fan of the formula because it's just one more formula I have to remember. Here's Dorner's method for doing this that doesn't involve remembering a formula, but just involves using a few colored pens. My thought process is this. The formal charge is going to be the number of electrons the element should have minus the number of electrons it does have if we take every bonded pair of electrons and say for the bonded pair, one goes to the atom on the left, one goes to the atom on the right. So let's try this with a few colors. Here are a couple of resonance structures that we have to decide if they're equivalent or not. So my thought process is this. I'm going to start with the oxygen. This oxygen currently has 1, 2, 3, 4, 5, 6, and one of the 2 electrons in that bond. Its neighbor, the nitrogen, has, in green, maybe I shouldn't use green, maybe I need something different here, something way different. In light blue, the other electron from that bond, those 2 electrons, 1 electron from that bond and 1 electron from the other bond. And the oxygen on the far end has the other electron from each bond in the double bond, plus these 4 electrons of its own. So I basically take the electrons in the Lewis structure and give possession of all the electrons to each element. And if there's a bond, one element gets one of the electrons, the other element gets the other. And then I think about what the element should have for valence electrons and what it currently has. So if I look at oxygen on the periodic table, oxygen's in the 6th column. This oxygen should have 6 valence electrons. At the moment, it has 1, 2, 3, 4, 5, 6, 7 valence electrons. If something has 1 more electron than what it should, then that thing is -1 because it has 1 more electron than it should. And now I deal with the nitrogen. The nitrogen is in the 5th column. It should have 5 valence electrons. 1, 2, 3, 4, 5 valence electrons. It should have 5. It does have 5. Things that have the number of electrons they should have no charge. And then out here to this oxygen, oxygen should have 6 valence electrons. 1, 2, 3, 4, 5, 6. It has 6. Formal charge on that one of 0. The overall polyatomic ion has a charge of -1. -1 plus 0 plus 0 is -1. Bingo. The charge on the ion should match the sum total of all the formal charges. Okay, I'm going to do the same thing to the next one. Those are the electrons that belong to that oxygen. Those are the electrons that belong to the nitrogen. And the oxygen out here on the end gets this one out of the bond, plus all of those lone electrons. And now I do the formal charge. 1, 2, 3, 4, 5, 6 electrons. Oxygen should have 6. It does have 6. Formal charge of 0. Nitrogen, 5th column, should have 5. 1, 2, 3, 4, 5. Does have 5. Formal charge of 0. Oxygen should have 6. 1, 2, 3, 4, 5, 6, 7. This oxygen has 1 more than it should. So that one carries a formal charge of -1. When I look at these two structures, I realize that they are in fact equivalent to one another. In both cases, I have 2 zeros and a -1. In both cases, the -1 lands on the oxygen. Therefore, if I have to decide if these are equivalent or not, these two are equivalent. These are going to be resonance structures. If one of them had come back better than the other, then we'd have to decide which of them was the more preferable condition. So one of the uses of formal charge is to decide if two resonance structures are equivalent to one another. These things are equivalent resonance structures. The other thing we can do is we can use it to check the arrangement of elements. Now, these down here are not resonance structures. These down here represent moving the atoms, not moving the electrons around. So we're going to use formal charge to decide what's the best way to do this. So working with your team, I want you to assign formal charges to each element in each of those molecules. So if I look at how this ended up here, in every case, the sum total of the formal charges I found adds up to -1. That's good because we're looking at a -1 ion. But then as I start looking at them, they're definitely not equivalent. This one is awful. I've got formal charges of -2, +2, and -1. This one does not win. This one is a little better, but it's not as good as this one down here. So if I had to pick the best way to do this, the formal charge situation says, do it like this. I have the lowest overall formal charges. The negative formal charge lands on the nitrogen, which is the most electronegative of the elements in the structure. This is the very best possibility. Now, early on, I gave you a rule that says when you arrange them, put the least electronegative in the middle. Look at that. Putting the least electronegative in the middle does, in fact, get you to the most favorable formal charge situation. Now, I want to use the formal charge to show you one more thing. When we were doing this before, I kind of gave you this rule that said when we're going to make multiple bonds, doing so with the carbon, oxygen, nitrogen column elements is best. I want to consider when we made this structure, we could have also, if I had not added any advice to this situation, we could have also made one that involved creating a double bond between the carbon and the fluorine, leaving the single bond to the oxygen. And so we could have created really two possibilities here. Now, I gave you a little bit of a heads up that making double bonds between the carbon, oxygen, nitrogen columns is the best case scenario. But now I can use formal charge to prove that to you. So I'm going to do the formal charge for these. So in this scenario, carbon gets credit for those electrons. Oxygen gets credit for those electrons. Fluorine for those electrons. And hydrogen, running out of colors here, gets credit for this one down here. If I calculate the formal charge in this situation, hydrogen should have one valence electron. It does have one valence electron. It has no formal charge. Oxygen should have 6 valence electrons. 1, 2, 3, 4, 5, 6, 7. It has a spare -1. Fluorine should have 7 valence electrons. 1, 2, 3, 4, 5, 6. It only has 6. It's 1 electron short. So it has a formal charge of +1. And carbon should have 4 valence electrons. 1, 2, 3, 4. Carbon has a formal charge of 0. Now this looks kind of good at first because +1 and -1 and 0 and 0 adds up to 0, and this has no charge. So that's good. But let's check the other situation to see if we can come up with a way that we don't have any formal charges. So here we've got fluorine getting all of these. Carbon getting those. Hydrogen getting this one. And oxygen getting those. Okay, hydrogen should have 1, and it does. Oxygen should have 6 valence electrons. 1, 2, 3, 4, 5, 6. and it does. Fluorine should have 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. It does. Carbon should have 4. 1, 2, 3, 4. Here's your better structure. They are not equivalent to one another, so we're not going to keep them both. When we think about whether we're keeping the whole collection or not, we only keep the whole collection if all of the ones in the collection are equally good. We're not going to do it, but we could go through the formal charge process with these 3 resonance structures, and we would end up being able to prove that all 3 of these are in fact equal to one another. That the oxygen ends up, the single bonded oxygen, with a -1 on each of them. The other 2 end up with a 0, but no matter how we do it, we end up with 2 -1s and 2 zeros, making all 3 of these equivalent and allowing us to say, yes, all of those are going to have to be shown because they are in fact equivalent structures.